Good afternoon, everyone. Now I want to show you on how to use this coupled area logarithm FEM model and to investigate the phase transformation and in the high-speed accordion of AISI 1045. So this is a coupled Euler logarithm. This is the FEM model. It's also called CEL FEM model. So now I'm going to show you. So this is my model. I'm going to walk you through the process. And here is the parts, and we have two parts. And one is a tool, and one is a workpiece. So here is a tool. So this is an open mesh. Here, this is my tool. Right? So the site. The site is here. This is a site. This is section. So here's the sites. There is one site now here. There's the whole body, and also the section assignments. And for this section, you must assign this section to this part to all the parts, and you have created. So this is a tool, and then we look at this is the workpiece. So this is a workpiece here, and also so this is my workpiece. So this is a predefined shape, and so here is this is my my workpiece. Right. So there's also one set here. Set is a set of this is a workpiece. Also, this guy and has section assignments. And then we go to the material. And material, this is material. So here is a tool material. So this is a tool material, and the tool material is a cemented carbide. So this is material properties are listed here. Conductivity, and so here is the conductivity. This is the density. This is a density. Here is a so this number of solution dependent. So this is elastic. Elastic Young's modulus. Young's modulus is this, and this is corresponding. This is Poisson's ratio. This is so expansion. Here is the expansion coefficient. And so this is here is a specific heat. So user defined field. We have this here. There's no data associated with this option. This option must be used in conjunction with the user subroutine, and we will use the VUS field for the explicit abacus, because this we are using the explicit, but we are going to use VUS field. This VUS field is written is written in the subroutine. So then we take a look at this is a material for workpiece. So material for workpiece for this is a conductivity is here, and suppose we have three phases, and so this is first one is for the three phases. So we have for this is low temperature. So for low temperature, so this conductivity, and this field means the phase one. Field one means how many phases you have here. And so for our case, we have three phases: 0, 1, and 2. So because for different phases, the conductivity value might be different. So it's also the temperature dependent. So you need to specify this one correctly. So density, the same thing. and for different phases 0, 1, 2, and we might have different temperature dependent mass density. Be very careful. This depth vary, the number of solution dependent state variable. This is inelastic. Also here, based on different fields, we have different temperature dependent Young's modulus along with the corresponding Poisson's ratio. So here is expansion. So expansion, temperature dependent. We assume this is temperature dependent also. So in elastic heat fraction, we use Poisson on +60, and we say a hardening user. So specify user. User means that so these hardening plasticity properties behaviors will be described in the user subroutine. So specific heat is a specific heat, a user-defined field, and as I said, we are going to use VUS field and for this explicit for this is Abaqus and in the user subroutine. So here's the material. So we are going to use Johnson-Cook model, and in this model, in this is modeling. So Johnson-Cook model will be written, and in the user subroutine. And then we section here. Section, we have section 1 and section 2. Section 1 is for the material, tool material. And so click this one, make sure this one is 1. And here, section 2, material workpiece, click this one, and here is 1. So this is section. And then we assemble them together, and you can see, so this is, we put them together, and you need to put them together here. So here is a predefined shape, and here is my tool, and here is this is assembly of this model. So here, look at here features. Here we have reference port 1, reference port 2, and the data datum system 1, the set, and we have several sets here. Left, so here this is left set, mid. So here is mid. Then we have several regions. I'm going to talk about this one momentarily. And so here's a tool, and here's a work piece. Here's the bottom. Right? Here's the bottom. So this is a curve, and curve is the curve, the tool tape on the tool. So curve 1 is the curve on the workpiece. So RP. So this is a slide. This is a slide here. A slide is a surface, machine surface, and the top. The top is on the predefined the shape, and tool. So here's a tool here, and workpiece here. So here is a set, and the surfaces. So left surface is the left surface, and the tool is a tool, right? This tool surface includes the rake face, and also this is clearance. This is flank face. This rake face, and so this, and also this clearance face, clearance angle, and these two curve, these are two straight lines. The top is on the bottom of the predefined shape and workpiece. So this is, and this one is corresponding to what I just told you. So, but this is this surface is on the shape, and also here is a machine surface. And then we look at so these the steps. We have initial step, And we have step one. Step one is dynamic temperature dependent explicit. So this time period is equals this one. So this is the option of this nonlinear in geometry is toggled on here. And we have, for this is a CEL, for this is a coupled Euler Lagrangian. This is the modeling. CEL, we have 4 regions. Okay, so 4 regions, or you can call regions or zones. And this is a zone A. So here is a zone A. Zone A is Euler mesh constraint entrance. That's the entrance. Entrance here. This is the material flows from this side. And zone B, and this is zone B. This is a Euler mesh constraint, zone B. And this is zone C here, so this area. And zone C is Lagrangian mesh constraint vertically, mesh constraint vertically. So it cannot move vertically. So zone D here, so this is on the chip. So this is Euler mesh constraint vertically. So this is, we have 4 zones here. Then we look at this field output request, and I'm going to show you what I have requested. So here I request this whole model evenly spaced time interval. This I showed it is interval here. And this field output requests and the history output requests. I'm going to show you what I have requested. So here, energy. Then, so I'm going to show you the arbitrary Lagrangian Euler adaptive mesh constraints here, and you need to have several constraints here. First constraint. So this is a constraint, okay? And so in the middle region, and U1, U2, UR3 are specified 0. So these are first ALE adaptive mesh constraints. And second one is here, right? And U2 is on point 2. So here, U2 equals 0.2 here. So this is the third one. Third one is on the left side. On the left side, and the material flows this way, from left to right. U1 equals here. U1 equals 0, and U2 equals 0. This is for this arbitrary Lagrangian Euler adaptive mesh constraints. So then talk about interactions, because the tool, the chip and the tool interact with each other. So we must specify the interaction. Before you specify interactions, and in the interactions, you must specify interaction properties. So let's look at interaction properties here. So here is the so the tangential behavior, normal behavior, and thermal conductance and heat generation, and this is my values that I have specified. So then, after you specify the interaction properties, you can create interactions. So this is interaction I have created. So here, surface to surface contact, explicit, and is on the tool, right? The tool and the workpiece, and these two guys are interacting with each other. So, and you need to specify, select the curve and select the tool, select the surface on the tool, and also select the surface on the workpiece. And so these two surfaces and are contacting each other. And so based on the interaction properties we just defined. And then let's look at the constraints here. We have one constraint. One constraint is that the tool is defined as a rigid body. Here, look at this is the so amplitudes. So amplitude 1, and so this is the tabular. We use the tabular amplitude, and so this is the amplitude and from 0 and 0.01, 0.1, and to 1. So this is the time. Right? This is the time, frequency time. This is amplitude. So we also have another one. And then we look at the boundary conditions. We have 6 boundary conditions. First boundary condition, and first boundary condition is for the bottom. Right, the bottom cannot move in the y direction vertically. U2 also cannot rotate around. This is the third. This is z-axis. So that's the reason we specify this one as 0 and this one as 0. And the second boundary conditions. And second boundary conditions. So for the curve, okay, and for the curve, U2 equals 0 and UR3 equals 0 as well. And third boundary condition, and for this curve 1, which is on the tool, on the workpiece, and U1 equals 0. U1 equals 0 here. This one, and this one is the slide, right? So here is the slide on the machine surface. Machine surface U2 equals 0. Cannot move in the vertical direction. So BC5 boundary condition 5, fifth boundary condition is on the reference point 0, 0, 0, and the tool does not move at all. So the workpiece is moving. So the relative motion between the tool and workpiece is accomplished. BC6. BC6 is left surface. Left surface, we specify our speed. So this is the velocity of the material flow. So as I said, in this model, the tool is being held stationary. So, but the workpiece is moving from left to the right. So as a result, the relative motion between the tool and the workpiece can still be accomplished. So this is boundary conditions. Then we look at the predefined field. Right? Predefined field, we have 2. And first one, predefined field, the constant through region and the temperature, right? The temperature we define 20 and 20 degree. So the predefined field 2, also the constant through region, the temperature for the workpiece. So this is pretty much about my model, and then I'm going to show you my simulation results. So this is my simulation results, and so you can see FE1 is for the phase the phase distribution. I'm going to show you. Let's click this one, Alt Feed View, and then we can just animate it. and then we can just stop at some instance, and then we can visualize the results. You can see 2, 1, and 0, 0 here. Okay, I'm going to show you enlarge this part, and so we can see clearly. We have several colors. This one color, this is blue color, and stands for this is blue color stands for the ferrite plus the chloride, and this is the red one. The green one is austenite, and the red one is austenite plus ferrite. So we can see we have 3 phases here. There's blue one, and the green one, and the red one. So this is FV1. This is phase transformation. This is the phase distribution. And then I can go to show you the temperature. So here, and the temperature is NT11 nodal temperature of nodes. So this is the temperature. We can see. I can show you show you an animation that is run. Okay. By the way, this is a tool. My tool is not the regular tool. It is laser textured the tool. So you can see these some grooves here. And then we can look at this. I'm going to show you the video again. So you can see clearly at the very beginning, and the predefined chip is thinner, and then as the tool, as the machining reaches steady state, so this is we can have a little bit thicker this chip. So this is pretty much and what I have, and for this is phase transformation and during this high-speed carding of AISI 1045, and using this is a coupled Eulalia Lagrangian FEM model. And I hope and so this this video is helpful for your either for your research or learning how to model this is machining and using Abaqus. And I hope you have a wonderful 2022. Bye everyone, and please if you have any questions, please leave comments. This is under this is a video, and this is a YouTube video. Bye.